Hi, I'm Kevin McDermott. Welcome to San Francisco. It's very nice to see you all in person. Yeah. So I'm going to do this as a tag team with a colleague of mine back in the UK, Simon, and he'll be joining us virtually if the technology works. Of course it does. What could go wrong? So I'm going to talk a little bit about the hardware-software co-design. A colleague spoke on Monday about the push-pull reality of some of the decisions that have to make through the complexities of building a processor, a subsystem, a complete chip. So, a few weeks ago, we celebrated the 50th anniversary, or the 50th birthday, of the microprocessor. And this is one of the ads from 1971. I really like the backdrop. You know, the mainframe computer was seen as what was the layman's view of a computer. And the phrase there was a processor on a chip, a computer on a chip, 50 years ago. I played a small part in some of these steps. So I wanted to give you sort of a retrospective of some of the things that I saw as a major events from that time. So they started off by claiming a computer on a chip. There was a little bit of a debate about some architectures. I won't elaborate too much on that, but there's a group that believes CISC is a good way to go, and then there's a counter-argument for CISC. I'm not going to make any comment. What I would say is you want to shift complexity. Do you make the software more complex for a simplistic hardware, or do you make the hardware more complex to hope that the software guys can really make use of every resource that you have available? Good debate. Let's see what happens next. Desktop computing moving into embedded. I used to say many years ago when I was doing custom ASICs that embedded was the unsung heroes of our industry. You know, instant on. You turn something, it runs, it works. They ship a product and it runs with software forever. There's no patches, there's no updates. Those guys, when they get to a deadline and they're shipping a product, they really test, or they're embedded. Obviously today it's a little bit easier. We've given them some internet connectivity so they can patch in the field, but they haven't lost that quality. Supercomputers, great academic applications. We might refer them today as a data center or cloud resources. Now this is great for software development because now you've got the freedom to explore multi-core, multi-processor opportunities, write your algorithms, scale across a very infinite resource. A little bit of a drawback, you know, there's not a supercomputer that's portable right now, and a little bit of cost and scale there. As I said, I was involved in many ASIC designs, and there's always been this debate between a standard product that you can optimize and build in mass production and then develop all your value on software, or should you look at your system design and optimize at the silicon level and do a custom ASIC unique for your application and targeted for your particular project. So there's always this trade-off. Should you go with standards? Should you optimize? Now today we can talk about the multi-core era. Now people have been talking about multi-core for 10 years. I was involved in the first dual cores going into mobile and the whole dependency on single thread performance and how you would scale that into 2 and 4 and 8 cores. We're way beyond that debate now. People are talking about systems of tens or hundreds or thousands of cores, split heterogeneously between worker functions, management functions, vector engines. This is the reality of today's system on a chip. But that's just the hardware bit. The software guys have been busy too. There's been a number of languages that have, again, don't want to be too controversial, but certain languages have ebbed and flowed over the last 50 years. Development tools, which is near and dear to my heart, help software engineers express and debug and develop the applications to run on these great new hardware. RTOSes and OSes are clearly a big development. Application software. Hey, this internet thing came along. Do you think it was going to catch on? Apps, and of course, let's not forget games. I'll come back to games later. So now I think I've got a word from Simon.
Hello, I'm Simon Davidman, CEO of Imperas. I'm sorry not to be with you in person this year. As we approach the end of 2021 and look forward to the year ahead, I'd just like to thank all our customers and partners and users for a great year with many successful projects. And if Imperas is new for you, then let me give you a brief company introduction. Interesting, for this year, the RISC-V Summit's co-located with DAC, and the history of processor and the semiconductor industry has a close symbiotic relationship with EDA. The best technologies running on the latest platforms help build the next generation. And the innovation of RISC-V is really at the center of the renaissance in custom processors, a way for system designers to optimize and co-design the next generation of hardware software solutions. And at Imperas, we believe the use of simulation in the hardware development can be complemented with simulation also to support software development. We're a 12-year-old company, self-funded and based in the UK. And at this event, we're going to be talking about two of our main product areas. The first area is our advanced simulation virtual platform solutions for software development, where we have a full capability and tools for debug, verification, analysis, profiling of emulated chips, platforms and systems, and software development tools for either bare metal, RTOS and full SMP Linux. And Imperas are a leader in the simulation solutions for software developers. The second area is RISC-V process development and verification, where we recently announced a new product, Imperas DV, which is a full RISC-V process verification environment. We spent the last 5 years working on RISC-V, and this new DV product is a culmination of our collective 100 years of DV experience and our team's over 10 years experience in working with customers on RISC-V processor DV. And if you're doing software development and need virtual platforms, or if you're developing RISC-V processors and need to get your designs verified efficiently and quickly, then please do talk to us. Talk to Larry, Kat, Kevin and Manny at the show and find out about how Imperas can help you get your quality products to market sooner. Also, if you want a bit of fun, please drop by our expo stand and have a go playing Quake on RISC-V. We recently ported this game to our RISC-V system simulator, and you can play it with audio, video, and interactively with a keyboard and mouse. Thank you. And now back to Kevin.
Great. Thank you, Simon. So yes, as Simon said, we've got Quake running on RISC-V downstairs, so please come and join us after the keynotes. So let's just talk about this hardware-software co-design. There's a great sort of theoretical challenge. If you want to sort of take a blank sheet of paper and think about what's the optimum system, you want the perfect hardware that's going to be dedicated with the right amount of resources, it's going to have the right capabilities, it's going to meet your cost goals, it's going to meet your power goals, and it's going to be completely bug-free. On the software side, you're going to have optimized software that has all the usability and capabilities. It's going to be written in such a structured way, it's going to almost self-maintain itself. And we are just in a glorious space here of hardware, software, synchronized and working together. Of course, as you develop each step, there's this whole, what you might call a chicken and egg situation. You optimize the hardware, that leads into more insights into what really is happening with the software. So you tune your software, which feeds back into how improvements into the hardware. So there's a bit of an iterative cycle. Again, I think theoretically, we think that's a good balance. There is an issue with iteration time. Initial hardware has to start, so you have to make some decisions. So a team of dedicated expert engineers would make some calculated estimates. You might call that a guess, but they'll make a first stab at a first order approximation. That'll lead into something that the software guys can get their hands on and try and look at some of their software partitioning and try and get some of this running. Not all the hardware features are available, not all the hardware features are functional, maybe not even debugged. So the software guys might write around or avoid some of those areas. That leads into you can't quite test everything, you can't quite debug everything, so you're kind of into this sort of waiting cycle. So there's an iteration cycle of one innovation stalls to get the next innovation to go along. And I think as we said earlier, the latest chips run last year's software really well. And that's sort of the innovation that's happened. But we were forgiven because we had Moore's Law. With Moore's Law, if you design a software that's a little bit pressured on the current chips, you could be forgiven because the next generation chip would run slightly faster. That only works if you equate performance to frequency. That stopped. So let me talk about another law. You might remember this from some of your grad school classes, Amdahl's law, which I think one of the popular phrases is it's more of a guideline than a law. When I was talking to people about this sort of 10 10, 12 years ago, going from single core to dual core to quads, people used to have this sort of symmetry where you take a single thread performance running on a single core, and you could say that's running at about 100% efficiency. If you go to a dual core arrangement, perhaps you can estimate that the second core is only going to be running about 50% efficiencies. As I said, a first order approximation, you're going to worry about some overhead. Then you go to third or fourth core. Fundamentally, you're really constrained by this single thread critical path. And this is where you get into this whole software hardware co-design. Because you started your software on a single thread computer processor, that's constrained you how you're going to scale into these multi-core arrangements. So what we're going to advocate now is that we start thinking about things from multi-core from the inception. So why RISC-V? Why are we here talking about RISC-V? Having an optimized processor is this fantastic balance of hardware and software. So you can have just the right features, just the right capabilities, extendable, but with standards. So you leverage all the ecosystem advantages and you optimize to just what you need in your application. So sometimes people talk about custom instructions in that it's going to help your end application because you can develop a better mousetrap with a better single instruction. It also allows you to think about your system design, not doing all traffic and communication through the front side bus of the processor. Maybe you have some side channels to a neighbor processor. In a multi-core arrangement, maybe you have a tight coupling between a couple of processors, maybe shared with another resource, and then those modules then communicate on a different basis to the other structures. So really it comes into optimized platforms. What we're going to see is heterogeneous designs where you have optimized at each level of activity, optimized control processors, optimized minion processors, the vector engines. This is all going to lead into custom hardware and the software compatibility. This is the great advantage of RISC-V. So let's talk about the modern application development. Working with cloud-based resources, you've now got a scalable resource. You can map your algorithm across a large compute array. This allows you the freedom to express in software different architectural choices given the infinite resources available in a cloud arrangement. You can also work with real-world data sets. So having collected a large amount of analysis, you can look at your algorithm running on a large virtual environment with real data. This gives you a great insight to the operation of your algorithm and how you might partition and develop. This leads into how you might develop the hardware to accelerate this. So there's two classes, really. You can think about a data center dedicated accelerator, or if this application is going to be deployed remotely in a field, then how would you develop this into dedicated IC and chips? As I said, let's introduce Imperas. We do virtual prototypes. We give you the freedom to innovate these type of architectural structures in software. So in a virtual platform, we can pick up the different architectural choices, the different configurations of these processors, and then run real software. The Quake demo is a good example of this. We're running a real-time application, interactive user experience with full audio on a virtual platform. Now, obviously, that's a trivial example just to show a game. But imagine if that was your flight control system, or if that was your automotive AI neural engine. Think about what that would give a freedom to your software developers to try these different system architectures. So this is an example. Some of our customers are a little shy and don't actually want to stand on stage and talk about the great work that they've done. So I'm going to take a bit of a liberty and I'm going to talk a bit about what they did. I'm not an expert in these systems, but what they looked at was around 150 cores split over a couple of arrangements with some vector engines running an AI machine learning application. They used our reference models and our virtual platforms to put together a model of this whole system, and they modeled at different levels of abstraction. So you model a minion unit, and then you model the whole system. They've simulated different workloads for different activities, and this allowed them the freedom to look at different architectural choices as their software was being developed. They had a year before they taped out their chip. That gave them a year, an extra free year to develop all this software. And you talk about any program management are always going to look at the software as the long delay that causes in some cases. And they were able to report when the silicon came back, they had their full workload to run on that device. So RISC-V really is this freedom to innovate. You've got the design options available that you can optimize across all layers of your architecture. And I believe this is the era of we don't have the one-size-fits-all anymore. So we optimize the right features with the right configurations. And I've got to say it, if you design a new custom processor, you have to also test it. And this is what I think is one of the shockwaves that's coming through this industry. If everyone's going to develop a custom processor, and this is going to be optimized across all of the industry, everyone's going to be a processor verification. Oh, sorry. Go back a little bit. I think Simon covered this in a little bit more detail earlier. Basically, this is a new product that we announced today, or Monday, Imperas DV. And if you come downstairs, we can give you a demo and talk about this in more detail. And then, so as a sort of a speech here to talk, what do we see as happening in the next, I don't know, 50 years, next years? Clearly, having an open ISA gives you this freedom to express different opportunities for the design. Standard extensions are going to be important. The software compatibility with flexibility is really the key part of everything we're doing around RISC-V. So I think we really are in this era of hardware-software co-design that can run across these multi-core arrays. And the prediction is that the ecosystem is now ready for this mass deployment on RISC-V. I think that's me, yes. So thank you very much. And I'll see you downstairs to play Quake. Thank you.